Go ahead.
Okay. Can you see the slides now in the full screen?
Yes.
Okay. Oh, hello everyone. Today I want to give you a very, introductory level talk about what is anti-set programming, and especially anti-set programming with Clingo. And the purpose is to just give you this idea and possibly, trying to have this added to your toolbox for problem solving, because it's very general and it's very handy. You can use it for whatever, and it's really great, as you can see. So basically, Clingo is a sort of declarative programming, and declarative programming is opposed to imperative programming. Imperative programming, like Python and C++ or whatever we have, is a program is that basically the program is an algorithm that we write to solve a specific problem. As opposed to that, declarative program is not an algorithm. It's actually an encoding of the problem itself. And the program only describes what is contained in a solution that we want. So for example, in our natural language, imperative sentence is that go to school, or versus the declarative sentence, which can be true or false, and that is I am at a school. So the difference is that we're not saying anything special to do, we're just stating the facts. That's basically our program. And there are some benefits to that. Of course, there are some drawbacks, like it's very hard to encode difficult problems in that way. But when it can be, it's very beneficial to use declarative programming, because first of all, it's very simple and high level. As you can see here, this is the solution to the famous 8-queen puzzles, where like we have 8 queens and want to put them in a board without them, being in the same column or row. And you can see that Clingo version, which is on the left, is just barely 4 lines, versus the Pascal coding is several lines, and it has like 4 loops and if and what have you. But the Clingo one, which I will get into what this notation means later, it's basically some facts that we have 8 queens and some constraints that they can't be in the same row or same column. And it's as simple as that. You just run this and it will give you all the answers, or the one answer. So there are different types of declarative programming. One is functional programming, which is based on functions and mapping of one number to another number. Another one is logic programming, like Prolog and Clingo that we talk about here, which is not functioned. It's based on 2 things. One is facts and the other one is rules. So here, for example, we have a fact that France is a large country, and we have another fact that France population is 65 million. And there's one rule here that says that any country that is bigger than France is considered large, for example. And one key idea to the Clingo is the idea of stable model. A stable model of a program consists of all the facts that are consistent to each other and that can be derived from rules. For example, here we have a simple code which have like 10 different values for P, and we consider a value to be large if it's larger than 5. And the first one is the fact, the second one is the rule. And you can see The structure of a rule is a head colon dash body. That colon dash sort of looks like a arrow, which says that if the body, then the head. And here we can see the results are all the facts that we know. The facts are the P1 to 10 and the large. And so that's, that's what a output would look like. It will give out all the correct facts. And so quickly, if I want to say, there are 3 different types of atoms. Clingo atoms mean the smallest, smallest thing that you can write. There are constants like francs or numeric constant like 1, and there are variables which are usually or always are with lowercase letters, here with X, and variables are used in rules. Lastly, one thing that we should know about the syntax is the choice rule. Choice rule is some rule inside the curly brackets, and it will, if you use a choice rule, basically you will have several stable models. So if you use these 2 facts that P of A exists and P of B exists without this choice rule, you will only have one stable model, which is P of A and P of B. But if you use them inside these curly brackets, it will produce all the possible sets with this, which is the empty sets, one of each and both of them. And the idea is that for later on, when we want to solve real problems, we will just produce all of our possibilities like this with choice rules. And if you have like several of them, their number of possibilities will multiply. So like here we have 4 stable models. If you have another one, 2, the total number will be 8. And so we have like a lot of these stable models, and then we start adding constraints to remove the ones that we don't want or that are wrong. And then this will reduce very quickly and will give our desired result very fast. And also, one last thing, we can specify how many of these predicates or elements we want this choice rule to have. For example, here we have 6 persons 1 through 6, and we want to elect some of them. If we use the choice rule without that specific number, it will be all of the possibilities, which is 2 to the 6, 64. But if we specify that we only want stable models with 3 persons elected, there will be 20 models, which is 6 choose 3. So the solving happens in 2 stages. The first stage is grounding. Grounding is basically turning all of the rules into the facts. A grounded fact is something that does not have a variable. So like here, P1 through 10, we saw this example for our facts, but the next one is a rule and has a variable, and that does not consider to be a fact unless it's grounded and we assign numbers to that X, which is 6, 7, 8. So after the grounding is what is called grounding is just turning that rule into those facts, and then on top of that, the solver will solve the stable model for us. One thing is that if you're not careful enough, this grounding will take a lot of time because it will output or it will consider all the possible combinations of the facts that we can produce, and we don't always want that. For example, here we have a sample, and it is a fact that every integer can be written as summation of 4 complete squares, and we want to know what is like the smallest number that can't be uh, written as summation of 3 completed square. One of them is like 7. You can't write 7 as a summation of 4 squares, 3 squares. And so like we want to find out anyway. So the code is here, like 2 lines, and we are just arbitrarily saying that there are 3 variables, I, J, K, and each of them can be from 0 to n. And the next line, we want to say that it can't be written as such. And as you can see here, solving this takes 10 seconds. And also we can see that the actual solving of this problem doesn't take more than 1 millisecond. It's the grounding that takes all that time, because we have n plus 1 to the power of 3 possibilities here that has to be grounded, and that takes a lot of time. If you want to reduce that, you have to be more careful. We have to use the symmetry of problem and set our rules more carefully. And also we have to avoid rules that has many variables. So for example, in this problem, we can use the fact that I and J and K can be ordered like this, in any way. And here, instead of stating that J is from 0 to n, we can say that J is from I to n, and K is from J to n. With that simple change, the time reduces from 10 to 2 seconds. And furthermore, we can use the fact that none of them can be bigger than the square root of the n, the whole number. And if you also add that, it will reduce to 5 milliseconds. So conclusion, if like it seems like it's hard to solve a problem with clingo or ancestor programming, maybe we can use this kind of tricks and reduce that, because we don't need all those unnecessary facts to be grounded. Another way to reduce time is to use multiple threads. So basically, ancestor programming used when we have intrinsically difficult problems that are NP hard. So in the worst case of scenarios, the solving takes exponential times, and like we don't want to wait that long. So we can use multiple CPUs and ask Clingo to solve this problem using several strategies. And the first one to find a stable model will be the winner thread. And we don't have to actually wait for the worst case. Another way to use parallel computation is to just split this computation between different CPUs, and basically it depends on the what kind of problems you want to solve. One could be better. So that was my introduction. Sergey, if you want to add something to that, can move to example.
Well, let's go move to examples, and then we'll see after you cover everything.
Okay. So here is one example of a problem we want to solve. The problem is that we have these 3 poles and there are 4 disks in one of them. We want to move them to the 3rd one, and only rule is that the bigger disks cannot be put on the smaller disks. So we, as I stated before, the program here is not an algorithm or anything, it's just encoding of the problem. So here is the facts of this problem. We have 3 pegs or poles. They have 4 disks. The initial state is that all of the disks are on pole A, and the goal is to put all of them on pole C, and we have 15 total moves. So here's is the solution, is the rest of the program. It has different parts. First, we generate all the moves that we can have. Then we test. Basically, that's the stage that I told you earlier, that we first produce all the possibilities and then we add constraints and removes the one that are not correct. I can go to details on this if you want. So quickly, if I want to go, it's like first, the first line, the second line, the generating part, it says that you have m moves in total, and at each time step we have one move. And if disk D is somewhere on one pole P, and we move it on that time, it will be placed on that. So as you can see here, it uses that choice rule that I talked about earlier, and it's specifying that it's impossible to have more than one moves at a time, and that's why the curly brackets is equal to 1. Then we move to the defining phase. The line 4 is just the mapping, doesn't really matter. The line 5, it says that it's turning the fact that initial state the disks are on pole A into another fact that on time 0 they're there. And then next line, it says that if we move something from one disk, from one pole, it will be on that, so on. And line 8 and 9 are the rules that the bigger disks can't be placed on the smaller ones. And that's it. That produces all the possibilities. And then we have the constraints that if a disk is blocked, it can't be moved, like line 11, and so on. So like we have to continue until the goal is achieved and so forth. And as you can see, like the solution that it will give us is like this. It will give us which moves we have to take at each steps. And it's one of the solutions that we can have. So that was a basic problem to just show you how it works. Now, I want to talk about how I've been using this in a real world problem. And so the problem that I've been working on is causal structure learning. And it's basically, we have a time series of some phenomenon, and we can turn that into a Markov chain of states that are affecting each other. And the degree of this Markov chain is 1, because if we think about it in a smaller time steps, nothing will be related to one time step before, just that state and nothing before that. So consider that we retrieve this causal graph from some time series. And the problem is that if the intrinsic causal time scale of that phenomenon, whatever it was, is faster than our measuring time scale, we will not be able to retrieve that true graph. For example, in the brain, if the brain neurons contract with each other like 10 times each second, and we use an fMRI to scan that and map that, it's only taking a measurement once every 2 seconds or so. So what we're looking at changes 20 times almost between each of our samples. So basically, we will have a very undersampled graph that we have lost a lot of information in between them, and we don't know what that was. And as a result of that, the causal relation could change. For example, in this graph, as you can see, the node 1 is connected to 2, and this same graph happens at each time, a real time step. So if you look at it twice as slower as it happens, in the real world, the 1 is affecting 2 and 2 is affecting 3, but we perceive it as if the 1 is affecting 3 directly. So the problem is to, given that undersampled graph, we want to know what was the original graph. And so one approach was that, do you have a question? Go ahead.
Sorry. Yeah, in the previous slide, can you, where you're explaining the graph. So basically you're saying that for the rank of 2 also, like the second one, it seems like it's exactly the same, but the only thing that's different is that the node 1 is also now attached to node 3 in the second one. So can you just explain that again, like how?
Node 2, look at node 2, that's easier.
Node 2 is
so
connected to node 3 and
yeah, so the thing is that because, as I said, if we look at it, if we consider time scale slow enough, the same relation exists at each time scale. So that part A of this picture that also exists on the next time step and the next and so forth. And if we stack all of them together in a row and we eliminate the times between the first and the last one, the relationships will change. For example, here, like 2 is connected to 3 and 3 is connected to 4. But we see that it seems like 2 is directly connected to 4 because we're looking at it slower than it actually happens. Did that answer your question?
yeah.
Okay, so one approach to solve this problem was using some recursive algorithm that we would first find all the possibilities of the initial graphs, and then we would search on that all space, and using some mathematical facts that we have, we would prune this searching space, and finally we would find several candidates that could have produced this undersampled graph. But the drawback of this approach is that it, first of all, is very slow, and it takes like 17 hours to compute a graph with 6 nodes. And secondly, it cannot handle graphs of bigger than 6. And also the code is very complicated. So now the second approach is to solve the same problem, but now with this answer set programming. So when we encoded this problem as answer set programming, we were able to get the exactly same results, answers, the same graphs, but instead of like 600 lines of code, it's now like 10 or 14 lines of codes. And also the time that it takes to compute is like 3 orders of magnitude faster. So here is the comparison. The blue ones are the graphs that have been computed using that recursive imperative programming paradigm. And the red ones are using clingo. As we can see, the same graph, which took around 1000 minutes to compute with the imperative programming, took only 6 seconds to solve here. And in the last slide that I have the encoding of this program, but I'm not sure if we want to go into that. Do we? Should I?
Oh, I don't know. What do you think, guys? I don't think we will understand the details, right, of what's going on.
Yeah, so basically the first 4 lines is describing what the graph looks like, the graph that is undersampled, and we don't know the original graph is look like. That's basically saying what edges it has. The next 4 lines, the one with the curly bracket that says, you can't see my pointer. Okay. Anyway, the one that says edge X and Y in curly brackets, it's saying that basically it's possible to have an edge between any 2 nodes. And here we're producing all the possibilities. And after that, in the last lines, we're reducing them. We'll get there. The next line is saying that if there's an edge between 2 nodes, there is a directed pass between those 2 nodes of size 1. And then the next line is saying that if there is a edge between like node Z and Y, and there is a directed pass between X and Z, it means that X and Y are also connected, but with length 1 plus the length of the directed path that we had. And so one thing that I forgot to mention is that when we undersample the graphs, like here in this, in the part B, node 1 and 2, they have a bidirected edge, and that's because they had a common factor that we can't see. For example, here, the gray node 1, the one in the middle, is affecting both node 1 and node 2. And this will show its effect as a bidirected edge between the 2 nodes. So here we are also saying that the same thing, but here about bidirected edges. And the last 4 lines are just the constraints that if we have a directed path in our nominated graph, we should have it in our undersampled graph as well. Same for the bidirected edges. And also, if we don't have a certain edge in that ground truth undersampled graph, we should not have that in our candidate graph as well. And that's basically it. We just, encoded the problem as simple as this, and it will reduce the time it took to compute that much.
Yeah, I love your as simple as this. I mean, it's easier said than done. Yeah, well, it took you a while, right? It took us a while.
Yeah.
Okay, so
it's hard. Go ahead.
I can add to this if you want, or maybe you want to talk a little more about motivating why anyone else would need that.
Well, basically any problem, I think that you have to search something. If you know what your solution would look like, you don't really need to search for it. You just, encode it here, and it will not even generate the inconsistent solutions. So it will be fast because of that. So it's not like that you will generate all the solutions, all the possibilities, and then find or search for the correct one. It will only generate the possible solutions. So if you're working on some problem of this sort, that you know what your solution should look like, but you have to search in a big space for that, this I think will help you a lot.
Yeah, so basically, this is a tool to solve combinatorial problems, and to not just solve combinatorial problems as solutions that satisfy the constraints, but also it can do minimization, optimization. You can specify the constraints not precisely to follow, but you can specify the constraints as you want to, get it as much as possible. So it can find a solution, the optimum that is nearest to what you specified. It's violating the constraint, but it's violating the constraint. You can add weights basically to your constraint. But why my personal dream desire is to introduce this as a tool in our group, as a standard tool in the toolbox, because, well, William gave a talk or discussion on this mixed integer programming, linear programming. And there, okay, if you spend time long enough to meld your problem into the setting of mixed integer linear programming, then you can pick up a solver that will possibly solve it quickly for you. Here with Clingo, similar to mixed integer linear programming, people have spent years, decades, trying to optimize the solvers in this approach. But the language is your general preposition logic, sort of first order logic language. It's very flexible. You're creating your own domain definitions. You don't have to think about very restricted form. It's still quite restricted, but you define all possible solutions, and you kind of generator. Basically, this choice constraint, I view it as, maybe I'm wrong, I'm not the pro. We had to, basically the heroic act of Sajad is for a year without any community, he was trying to figure out how this thing works and how it's the community is minimal. It's not like deep learning. And in deep learning, everyone is struggling with the same minimal problems. In answer set programming and in Clingo, it's only people who understand everything that they already work in there. So you cannot find and ask elementary questions. So, well, read this paper. Those are the interesting questions. So that was hard. But other than that, if you have a combinatorial problem and you're thinking of writing your solution for that, or you're thinking recalling some words like branch and bound or something like that, forget all of that. If you see a combinatorial problem, come talk to us. In Clingo, it's very easy to write once you know how to write it, and it's super efficient. And it comes down to this paradox that we've discussed on your talk, William, at the time of your talk, that yes, we are dealing with NP hard problems all the time in PCBs, like optimally connecting, or trying to optimally connect the elements on the board, and in other similar problems. But yet, with those solvers, almost all of them, problems with million elements, which would be 2 power million, if we go with the worst case of the brute force of the search. But we're solving them in seconds, or okay, in days, but most of the problems that we're encountering in practice in those NP hard problems can be solved by solutions like answer set programming. Well, maybe I shouldn't say most, I can't quantify that, but a surprising amount, like overwhelmingly surprising amount. And as Sajad said, there's this problem that he said we got 3 orders of magnitude improvement. The paper and the code was from 2015. And well, maybe I'm jealous or so, but we're still not as general as that approach, but because that other approach ignores the value of maximal undersample, we have to set it with clingo and we slow down when we set it too high. But in any case, 3 orders of magnitude, and it another advertisement, not just the speed, also part of the grant proposal that I wrote for that and got funded anyways, was, okay, we can solve, or at least we know how to solve in a graph with strongly connected components. We can handle one strongly connected component. And the proposal was many graphs can be split into multiple strongly connected components, and we can figure out how to exploit that in order not to solve for the large graph, but to solve for the smaller graphs and then join them together, and that would be efficient. We don't know how to do it, but that's a kind of a way to go. It not even a single additional line to the clingo code turned out to solve that problem. It was a very small modification of the code that Sajad mentioned, that we can solve 100 node graphs now, whereas in 2015 that was 6 is the maximum, but by exploiting that strongly connected component. And very easy, you can scale up and you can solve problems that were not addressable. And another thing automatically also we could address with this approach is that what if you change the settings and collect more data at even slower sampling rate, because you can slow down your device. You cannot speed it up because otherwise it would be already at high speed. Like in fMRI, what if we collected data at 2.5 seconds sampling rate in addition? Could we learn more? And we have reasons to believe that we could, but how to implement that also was very easy. So you like think about problems of combinatorial sort and think about clingo, and it's very easy to use and super fast.
I guess I have a question. Maybe you wouldn't want to cover this, but just out of curiosity, can you give like any small explanation of how the solvers are working behind the scenes, like as high level as you want, or feel free to reject that because I know the solvers are complicated, but I'm just curious.
Well, Sajad already kind of tried, right? But in the beginning at high level, but maybe, do you want to try again, Sajad?
Yeah, I want to show that. So here, like here's a very small example, and like, you know, it has one fact, P1 to 10, and one rule, large X. So this large X could be anything, right? So this is not solvable because X, we don't know what X is. But then at the body, we said that X is whatever that is inside P. So then the grounder will produce large 1, 2, 3, 2, 4 to 10. Then we have another constraint that X is larger than 5. So the solver looks at the grounder. The grounder has all of the large possibilities, which is 1 through 10, and removes the ones that are conflicting with our rules. And that's basically how it works. So here in the graph example, we first produce all the possible edges that we have. The grounder will produce all of them, and then it will look at our constraint. So here we have an edge that does not exist in our ground truth. So it will remove that from our, if we remove that actually from that whole stable model. So if you remember, I said that when we use curly brackets, we use choice rules, we will have multiple stable models because each of them could exist or could not exist. So here, if you have edge in a curly bracket, it means that among all the edges that we have from any x to any y, it could exist or it could not exist. And each one of them is a possibility, is its own stable model. So the grounder will produce all of that. And whenever there is one conflict in one of those stable models, it's not stable anymore. So it does not produce that. It will only give you the stable models that are consistent with everything. So that's how it works. Yeah, and also, Jerry mentioned we can use optimization for this. I didn't add this here, but consider that in this graph example, we have a undersampled graph that we are very certain that some of these edges exist, and we're not very certain that some of the others exist. So we'll assign weights to that, and the clingo, instead of giving us all the possible stable models in that situation when we use optimization, it will optimize based on what constraints are more important to us. And taking all of them into account, it will only give us one solution. So that's one difference between optimization and regular one, is that it doesn't give us multiple answers anymore. It gives us one optimal answer.
So another interesting point is that those are solvers of discrete problems. Can we port them to deep learning problems? Right? Can we generate candidates or starting solutions, or can we write a codex module that from my verbal description of the code generates clingo code, and I run the solver then, because I can tell the conditions of Tower of Hanoi puzzle, but encoding it is a pain because I need to know the language and everything. So that could be interesting. But one of the initial questions when deep learning was starting, when the hype about deep learning was growing at IBM Watson, somebody asked me, I was giving a talk on this early applications that we were playing with, and they asked me, well, this is all continuous, but can we solve discrete problems with deep learning? Can we generate graphs, optimal graphs and things like that, so that are combinatorially defined? So I don't know if we need to apply deep learning to anything, but this is a tool that is already fantastically optimized and useful. So it's more of an advertisement of this approach. Well, anyways, I think we're done early today. Right, Sajad, do you have more material or?
No.
Any closing remarks?
Well, I'm still learning myself. So there's like this book that I use for this presentation. I'll add that to the references and share these slides. And there are some interesting things, like you sent me the paper of that partial grounding. I won't learn that. And so I think there's a possibility that you don't have to ground all of these facts at once. There's a way to be more specific, and that will probably help, but I don't know that yet. So it's not just like, it's a very simple one. If you seriously consider using this, there's way more to this, and it's much more efficient than this.
Okay, so Alex says avoid deep learning, use clingo. That's my reading of whatever comes up in the chat. And I think we're done for today. Ashkan was supposed to present next week on, he's not here, on physics of higher order interactions in complex systems. So let's see, that's next Friday. But I will stop the recording.